Hey everyone, and welcome to this explainer. Listen, if you're a focused learner looking to master the absolute essentials of mathematics without all the unnecessary fluff, you are in the exact right place. Today, we're taking out a subject that, let's be honest, often strikes fear into the hearts of students everywhere. Yep, we're talking about trigonometry. But do me a favor, completely forget any anxiety you might have associated with that word. We're not going to look at it as some scary, abstract math concept. Instead, we're going to frame it as exactly what it is: a simple, highly predictable toolkit used for measuring the physical world around us.
To really understand why this toolkit was even invented in the first place, think about this for a second. How do you measure a mountain you can't physically climb? Or, how do you figure out the exact height of a massive skyscraper without dropping a giant tape measure from the roof? It sounds pretty much impossible, right? But with the simple decoder ring of trigonometry, these complex, real-world measurement problems become completely solvable. All you need is one distance and one angle. It's almost like a magic trick, but it's just math.
So, here is exactly how we're going to break this all down today. Section 1, the right-angled triangle. Section 2, the 6 trigonometrical ratios. Section 3, understanding reciprocal relations. Section 4, ratios of standard angles. And finally, Section 5, solving complementary angles.
Let's dive right in with Section 1, the right-angled triangle.
Before we even think about throwing formulas around, let's break down that intimidating word. Trigonometry actually comes from Greek words that literally just translate to the measurement of triangles. That is it, the whole shebang. In this explainer, we're dealing exclusively with the relations between the sides and the angles of right-angled triangles. Honestly, it instantly becomes way less scary when you realize it just means measuring a basic three-sided shape.
Okay, now as we start looking at angles, you're going to see some symbols that might look like an alien language. You'll see things like theta, phi, alpha, beta, and gamma. I want to assure you right now, these are literally just placeholders. Just like you might use the letter X or Y in algebra to represent an unknown number, trigonometry uses these Greek letters to represent unknown angles. So don't let them throw you off. They just mean some angle we happen to be looking at. Now let's look closely at the actual anatomy of our right-angled triangle. It has three sides: the hypotenuse, the base, and the perpendicular. The hypotenuse is the easy one. It's always the longest side, sitting directly across from the 90-degree angle. But here's the absolutely crucial point. The base and the perpendicular can actually swap places. It all depends on which acute angle you're using as your starting point, which is what we call your angle of reference. The side directly opposite your reference angle is the perpendicular. And the side right next to it, that's your base.
Moving right along to Section 2, the 6 trigonometrical ratios.
We're about to introduce some terms that sound super advanced, but I want you to keep this one simple rule in mind. A trigonometrical ratio is nothing more than a simple fraction. Really, it's just the ratio between the lengths of a pair of two sides of a right-angled triangle. You're just taking the length of one side and dividing it by the length of another. Simple as that.
And that brings us to our first three main tools: sine, cosine, and tangent. Sine, often just written out as sin, is simply the perpendicular divided by the hypotenuse. Cosine is the base divided by the hypotenuse, and tangent is the perpendicular divided by the base. And because these ratios are literally just dividing one length by another length, the final result is just a real number. It doesn't have a unit like inches or centimeters, it's just a pure ratio.
So how do we actually use this in practice? Well, if we know two sides of a right-angled triangle, we can always find the third side using the Pythagorean theorem. Let's say the hypotenuse is 13 and the base is 5. We just square them. 13 squared is 169, 5 squared is 25. Subtract 25 from 169 and you get 144, and the square root of 144 is 12. Now that we've solved for that missing perpendicular side, which is 12, we can easily calculate any trigonometrical ratio we want. We have the whole puzzle.
Which leads us perfectly into Section 3, understanding reciprocal relations.
Okay, so we know sine is the perpendicular divided by the hypotenuse. Well, I want you to meet its twin, cosecant. Cosecant is literally just the sine fraction flipped completely upside down. It's the hypotenuse divided by the perpendicular. In math terms, they're reciprocals of each other.
And the beautiful thing is that exact same logic applies across the board, giving us three pairs of reciprocal twins. Sine pairs with cosecant, cosine pairs with secant, and tangent pairs with cotangent.
Think about it. If you know the tangent is perpendicular over base, then you automatically know cotangent is base over perpendicular. Mastering the primary 3 tools gives you the secondary 3 entirely for free.
And because they're reciprocals, a wonderful piece of mathematical magic happens when they interact. If you multiply a ratio by its reciprocal, for example, the sine of an angle multiplied by the cosecant of that exact same angle, the numerators and denominators perfectly cancel each other out. The result is always exactly 1. No exceptions.
All right, let's look at some real numbers in Section 4, Ratios of Standard Angles. Think of this standard table as your ultimate decoder ring. In trigonometry, we frequently work with what we call standard angles, 0, 30, 45, 60, and 90 degrees. Mathematical constants dictate that the ratios for these specific angles are always exactly the same. For instance, the sine of a 30-degree angle will always be 1/2. The tangent of 45 degrees will always be 1. Having these specific values mapped out is a huge time saver. It means you don't have to calculate them from scratch every single time. They are fixed, super reliable properties of geometry.
But wait, notice the hidden pattern within that data. If you trace the values as the angle increases from 0 to 90 degrees, you're going to see a really fascinating inverse relationship. The value of sine steadily increases from 0 up to 1. But simultaneously, the value of cosine does the exact opposite. It decreases from 1 down to 0. Recognizing this elegant mirrored pattern makes memorizing these standard values incredibly straightforward.
And finally, we arrive at Section 5, Solving Complementary Angles.
The definition we're working with here is beautifully simple. 2 acute angles are complementary if, when you add them together, they equal exactly 90 degrees. Now, because any triangle always has a total of 180 degrees, and the right angle takes up 90 of those right off the bat, the other 2 angles in our right-angled triangle absolutely must add up to 90. Therefore, the 2 acute angles in a right triangle are always complementary. If one is 30 degrees, its complement has to be 60 degrees.
An understanding that brilliantly illustrates why it matters for our ratios. Let's visualize a triangle for a second. If we focus on angle theta, its sine is the perpendicular side over the hypotenuse. But what if we swap our perspective to the other angle, which is 90 minus theta? For that new angle, what used to be the perpendicular is now the base. So the cosine of that complementary angle is the exact same fraction. Through this geometric logic, we see that the sine of one angle is exactly equal to the cosine of its complement.
This gives us our final set of interlocking relationships to complete your new measurement toolkit. The sine of 90 degrees minus theta equals the cosine of theta. The tangent of 90 degrees minus theta equals the cotangent of theta. And the secant of 90 degrees minus theta equals the cosecant of theta. These aren't just arbitrary equations you have to memorize. They represent the perfect interlocking geometry of the right-angled triangle where every single side and angle exists in total harmony with the others. And just like that, that brings us to the end of our explainer. We've gone from a simple 3-sided shape to a full, reliable mathematical toolkit. So I want to leave you with this final thought today. Take a second right now to just look around the room you're sitting in. Spot a right angle. Maybe it's in the corner of your window or right where the wall meets the ceiling. Knowing what you know now, what invisible, perfect trigonometrical ratios are holding up your ceiling at this very moment? The world is really just a series of measurable, interconnected triangles waiting for you to decode them. Keep learning, keep observing, and I'll catch you next time.